In the first lesson, I told you that I was excited about AFM. One of many reasons is that it has very good resolution. Well, it's not the only instrument that you can use in nanoscience, nanotechnology, that has resolution that's very good, better than an optical microscope. One of the alternatives is a scanning electron microscope. So in this lesson, let's talk about how AFM compares to SEM, scanning electron microscopy. So firstly, let's make sure you know what an SEM is. In SEM, what you have is a filament of wire, maybe a sharp tip of wire. You run a current through that, and in this filament here, electrons boil off. And what you do is you apply a high voltage between this filament and a grid, and so the electrons are accelerated toward that, and then there's a focusing mechanism similar in principle to an optical lens, and the electrons are drawn through that and then focused onto a sample, and in the sample they're fairly high energy, and so in the sample they sort of cause a little bulb of excitation, and some of the electrons sort of make their way to the surface. They're low energy and they're collected by what's called a secondary electron detector, SED. All of this is in a vacuum, and I'll represent that by this square rectangle like that. And in order to form an image, what you do, similar to AFM now, is you raster that electron beam in the X and Y directions, and the secondary electron detector sends its signal to a computer, and you get an image of the sample like that. So this image is the current from the secondary electron detector as a function of the XY position of the beam. So note what's going on here, that everything is done in a vacuum, and because the probe is a beam of electrons, if that sample were not conducting, all the electrons would collect. And you know that like does not like, right? Like charges repel, and so if the sample is not a conductor, this system will not work. So you must use conducting samples. And typically, if you have a non-conductor, what's done is you coat the non-conductor with a thin layer of a conductor, gold, for example. So that's a disadvantage, but what you can do with these electron beam steering optics, those are very nice because it's very fast. You get real-time data acquisition, and it's very maneuverable, such that there we go, such that you can get an image of the entire sample, like on the order of centimeters, and then you can get features on the order of nanometers. So that allows you a tremendous magnification range. So SEMs are very nice complements to AFMs. They do tend to be more expensive than a typical AFM. And so now in the next slide, let's list the advantages and disadvantages of AFM in light of the scanning electron microscope. So here, I just put up a little visual reminder of an AFM with the cantilever, the laser beam near a sample surface. And let's say, okay, well, what's good about AFM? Well, first of all, you don't have to have a vacuum. Yes, you can do AFM in vacuum, but you can also work in air and also in liquids. All right, biologists really like that because you can study living cells. The sample can be a non-conductor, or can be a conductor, a semiconductor, as you will. And whereas in SEM, the image that you get is just the electrons that come out, in AFM, it's possible to get an accurate vertical measurement. Right, so you can get the features, height, in an AFM. And then, because you don't have to be a conductor, the sample prep is easy. What are the disadvantages? Well, let's list them. There's a limited Z range. So most AFM scanners cannot accommodate height changes of more than a few microns. And also the magnification, the lowest magnification, i.e. when you want to see all of the sample, well, you just can't. You can only see maybe 100 by 100 microns at a time. Whereas in SEM, you can see up to about a centimeter of your sample or so. So many AFMs, you use an optical microscope to see where the cantilever is over the sample, and that adds some complications and expense. Let's do a side-by-side comparison now. Let's say we have an AFM sample with a sharp feature in it, and here's our AFM tip and contact. Now think about how that tip is going to pass over that feature. The path it will follow will look like this, right? Because the tip has finite width. In a scanning electron microscope, there's actually an equivalent phenomenon. Here's our beam of electrons. Here's the sort of bulb of volume that it excites. And some of the lower energy electrons make it to the surface and are collected. And so this is equivalent, isn't it? The beam excites a finite width. And in AFM, you know that the pressures can be high. We made that point in lesson 1. And that can cause damage. In SEM, the energies of the beam can be high. Right? So kilovolts. And if you've got a delicate sample, that can cause damage as well. So, in other words, AFM and SEM have some similarities as well as different advantages and different disadvantages. So if you're going to do nanoscience, nanotechnology, it's nice to have both instruments, so such that you can take advantage of all the good things about each of them.